Hi, it's Robin. In previous videos, we started looking at Hal Laboratory's LeMans game for the Commodore 64, which is an unlicensed clone of Sega's Monaco GP, and it was a launch title for the Commodore 64 in 1982. I love the game, but have long had a suspicion that it either has a bug or it outright cheats. I wanted to disassemble LeMans code, but none of the machine language monitors I have are able to examine a self-booting cartridge like LeMans, so I spent the rest of the first video figuring out how to dump the Ultimax mode cartridge to a file. Then in the next video, I figured out and demonstrated how to turn that raw binary dump into an executable C64 program file so that the game could be simply loaded and run without going through a series of incantations. With those tasks out of the way, that brings us to the present, where we can finally start looking through the code of this game to figure out how the scoring and time systems work and see if we can't uncover the secret behind this game. Okay, so now we have the game running. Now, on to finally look at my at the mystery a bit here. Okay, so I'm just going to go again to the Super Snapshot Monitor, which was kind of the whole point of that exercise. So even a game that's only got an 8K ROM like LeMans, there's actually a lot of code involved. Like we were saying, it starts at E1000. I could just scroll like this. Okay, there, now we're up to E100, so we're through one page of code, so to speak. Just really give you a sense of context there. We're through 2 pages now. And this goes all the way through E1000, E3, E4, all the way up to EF, then into F1000. And while some of this is going to be graphics data and other data, well, right there we're looking at, I think, probably some level data, some map data. Most of it is code. So there's a lot of it. I've been scrolling all this time, and we haven't even looked at maybe a quarter of the code yet. I think that's some scroll code there. Scrolling the screen. Okay, so all that to say, we're not going to look at all the code today. So what I've done instead is I'm just going to walk through the particular path where I think the time is cheating, so to speak, that you have 60 seconds to race, but a second isn't truly a second. A second becomes much shorter as the game goes on. So we're going to try and walk through the relevant code just for that path to understand that better. So the first place we're going to look is at EE10 hex. We're going to just disassemble that. And this is something you don't see in a lot of games. Set decimal, and that sets the 6502 decimal mode, which really isn't used all that often. But I did make a video about using decimal mode for game scorekeeping, so I'll put a link in the video description for that if you want to watch that. So I won't get into in great detail here, but this is the part of the game code that as you drive, your score just keeps counting up just as you drive. And that's exactly what this does. So it's actually 3 bytes, but binary coded decimal bytes. And the low byte is stored in 0 page at 0A. One thing to keep in mind while looking at this game is that this was coded for the Commodore Max, which only has 2K of RAM. So it's going to especially use a lot of 0 page RAM, because all it has is 0 page, the first 256 bytes of RAM. Then it has the stack space from 100 to 1FF hex. And then it'll have the 200 page, the 300 page. And then it has screen memory from 400 up to almost the end of 7FFF, except for the sprite pointers and a few unused bytes up there. And that's it. The RAM's already done. 2K total. Okay, so the score here is stored in OA. And here you can see it adding 1 and putting it back into the low byte. And the rest of it, it's just going to load each one, add 0, and then store it. Kind of strange that they didn't use increments and branches, as I think that would have saved 2 bytes per digit. But anyway, this is how they did it, and then decimal code is over. Now, maybe I'll show a little insert or something, or while I was playing the game, you might have noticed that the score actually counts up by tens, but this is only incrementing by 1. It's actually cheating. When it displays the score, it's putting a dummy 0 at the far right and the least significant. So as far as the actual game code goes, it's only adding 1 point at a time, but to us it looks like 10 points at a time. But that's a fairly common cheat in games where they'll put a fake 0 at the end of the score just to make your score look bigger without actually consuming a byte or even a nibble. Well, a binary code decimal means there are 2 decimal digits packed into 1 byte, each 4 bits of a byte, each nibble, which actually have 16 possibilities. Only 0 through 9 are used. And the processor takes care of when you add 1 to a 9 in BCD mode, it automatically changes that to 10 hex. I guess I should explain that. Normally a hex digit can go from 0 to FF, and that can include values like 1F. So normally when you go from 09, if you increment that, you would go to 0A in hexadecimal. But in BCD, instead of going to 0A, it automatically fixes it and changes that to 10 hex, but it's binary coded decimal. So we can call this 10 in BCD. Even though it's stored in a hex byte, we read it as if it's decimal. So we discussed earlier that every 20,000 points, you get extended time. So after the score is being incremented by 1 here, it's possible that we've rolled over to 20,000 points, actually internally 2,000 points. It's going to be confusing. So to check if we rolled over, it's going to load 0A, that's the least significant byte, and if it's not equal to 0, then it's just going to jump ahead because it knows the last 2 digits have to be 00 for it to have rolled over 20,000 points, or it's actually every 20,000 points you get an extended time. So it's going to check, are the last 2 digits 0? If not, for sure, there's no extended time to be awarded. Here's like a really clever bit. Next, it looks at location B, which is the middle 2 digits. And again, 20,000 points is actually 2,000 points internally in the representation, 2000. So this would have to be 0. And this would have to be 20. But instead of comparing it with 20, it does something really clever here. It ANDs it with 1F. And then branches if not equal ahead to EE35. Why doesn't it compare with 20 hex? Well, it doesn't do a comparison with 20 hex because if so, that would only show that you've scored 20,000 points or maybe 120,000 points, but it doesn't handle the case of 40,000, 60,000, 80,000, 100,000. But this does somehow. So let's look at how that works. So if we've got 20,000 and you AND that with 1F, well, 0 and F equals 0. You know how ANDs work? Let's break this down into bits. For AND, it's only true if both of these bits are 1. So obviously 0 and 1 equals 0, and these all equal 0. Therefore, this is 0. Okay? So only if any of these are 1, then that would be true here. But it isn't. Okay, and so 20. Okay, now we're looking at the leftmost bit. This 2 in binary is like that, and the 1 is 0, 0, 0, 1. Let's add those together. 0 and 1 is 0, 1 and 0, 0. Well, those are all 0. 0, 0, but the code branches if it's not equal 0, therefore this is true, and 53 is incremented, and I can tell you right now that 53 is the number of extended times that you've earned. So if you've got a 20 in there, the code will increment your extended times by 1. Are you convinced yet? I know this is kind of weird. What happens if we had, say, 21 in there? 21 and you end it with 1F. Would the code execute? Well, if we had 21, that would be the same as 1. We're just looking at the rightmost digit here. 1 and F. This is binary for 1 and F. And that equals 1 and 1111 equal 1. So our result is 1. And we can already see that this is not 0. And therefore the code would branch past and not increment our lives counter. What happens if we have, say, 30 in the score? Well, we already know that 0 and F would be 0, but how about this space? Well, that would be 1, 1. Again, look at the left values here, 3 and 1. This is those values in binary, 1. So this is not equal to 0, therefore branch of not equal to 0 ahead to EE35. Sorry if I'm belaboring this. This is pretty confusing to me. Okay, but let's look at the last case here. What happens if we have 40 in the score? Surely this won't work, will it? Okay, well, 0 and F is 0, 0, 1, 0, 0. Now we're looking at the left nibble here. 4. This is 4 in binary. And 1. Compare those. And you get 0, 0, 0, 0. 40 and 1F is 0. It is 0, therefore this will be incremented. So that kind of blows me away. It's like, this is one of the most clever things. This amazes me that a single compare or single and can be true every 20,000 points, for example. Like that works. You don't have to do. If I had to program every 20,000 points, I probably would have tried to divide or shift it or, I don't know. I'm blown away. Maybe I'm just really simple-minded or something. Maybe this is obvious to everybody. That is the coolest trick. Okay. Well, that's just one little segment. Moving on to the next one. That's where the score gets incremented as you drive. Here's the next one. F3, 9E. Here's more code. And now instead of starting at A, which is the least significant byte, we're going to start at B. We're going to add 1 to that byte. So that's the equivalent of 1,000 points. Well, this is the code that's run every time you pass 10 cars in a row without crashing, you get 1,000 bonus points. So that's what this is doing here. Really, internally, it's 100 bonus points because of that false tailing 0. So it just adds a 1 to the middle and to the highest, the most significant byte. It does the add 0 and stores it. So that's just increasing the score, incrementing the score again. And it does exactly the same 1F trick. So I don't need to explain that again. But it's so cool. And the end result is 5-3. Location 5-3 is incremented again if the score hits 20,000. Every 20,000 points, you get an extended time here in this counter. Okay, so that's all the scoring. That's how you earn extended times. What's next? Well, now we're going to look at how time is decremented. So first we're just going to look at location E182, and this little snippet of code. This is just initializing a couple of the variables. 3C hex is 60 decimal, and it stores that in location 18. Location 18 is ticks per second. That is how many internal game ticks, and it runs at about 60 a second. We'll look at that towards the end of the video. But basically the game is ticking away, as most video games do, in fractions of a second. A very common value is 60 times per second. Even if the screen is or isn't updated 60 times a second, 60 frames per second, 60 hertz, there'll be an internal system that's updating the physics, the game movements in 60ths of a second. That's not universal, but that's a very common factor. Even 40 years ago, lots of games ran at about 60 frames a second for the game logic. So 3C, so that means internally there's a counter, and a second lasts 60. At least it does at first. Now, here is 60 hex stored in location 16. Well, this is the actual time counter that you see on the screen that starts at 60, counts down 59, 58, 57. It's in binary coded decimal, which means it looks like a decimal number even though it's stored in binary or in hex. 60 decimal seconds, binary coded decimal, and that's in location 16. So that's the actual timer that counts down. So that's where the two are initialized. 60 ticks per second, 60 seconds per gameplay until you get game over, unless you get an extended time. That's where those are initialized. Now the next bit of relevant code is at EFEE, and that's where it loads from memory location 16. These are 0 page, by the way. It's just an 8-bit address. The first 256 bytes of memory are called 0 page, and they have a special addressing mode that allows them to be read quicker. It only takes 2 bytes of code here. This is the machine code. 2 bytes of code to read that location instead of normally it takes 3, plus it saves a cycle, processor cycle. So that's very valuable RAM. Okay, so it's going to check if the time is equal to 0, and if it has, it's going to branch ahead way down to here. And otherwise, it has a counter here at location 17 that's going to increment, and this is the number of ticks per second. So this is incremented every single tick, and if it reaches 18, that's the ticks per second, which is, say, 60, well, 3C hex, which is 60 decimal. If it's less than that, then it just branches ahead with the incremented counter. So if it hasn't reached a full second yet, it just continues on its way down here, F00B. But if the ticks has reached the number of ticks per second, say I've counted up to 60 60ths of a second, roughly, then it's time to set decimal mode and actually decrement, subtract 1 from the current timer. Okay, so there's the on-screen timer, which is counts from 60 down to 0 seconds, but internally it also has these other 2 counters that are counting up to 60ths of a second. And this is pretty common in games. Okay, and the important thing here is if time did reach all the way down to 0, then it's going to branch to this F0007 or F007, which is here. And it's going to put a value of 1 into location 12, and that is a game over flag. That means that you've run out of time, and we're setting a flag. That means the game is over. It doesn't immediately jump to that, it just sets a flag. And that's pretty common in game code, where you've got this game loop running over and over again, and rather than interrupting that game loop, which you kind of need to keep going because it's probably doing things like scrolling the screen or playing sound, other things that you don't want to just abruptly end, instead you set a flag, and then a different part of the code will check for that flag and deal with it when the time comes. Okay, now that flag is checked in many places, and we can do some if we hunt through memory from, well, this is the whole game code from E000 to FFFF. If we check, A5 is the machine code for load A, 0 page, location 12, and then a branch. Basically, this is a sequence of bytes that you could figure out by assembling it yourself, by just happen to know it. And if you search through memory for those, you'll find these different instances where location 12, that game over flag, is checked. And there, just printed them out on screen. And if we disassemble them, EC7A, there's actually quite a few occurrences of it, but in every case, the pattern's the same. Load, location 12 hex, branch, if it's equal to 0, that means not set, branch ahead, but otherwise jump to this subroutine, F462. We can look at a couple, we can look at the others here. ED36, same deal. You load it, check, branch ahead, otherwise go this routine, F462. Okay, so that's where we're going to look. That's the game over routine. F462. And here it is. Okay, this is a little bit odd here. It stores Y and X temporarily off in these locations. I don't see why that's necessary. That might be some old code that just kind of got left in there and never cleaned up. But anyway, Y is stored in 56 and X is stored in 57. But here's the important part. This is the game over routine, so to speak. But the thing is, it's not necessarily game over because it's going to load location 53, which is that counter counting the number of extended times we have. And if it's equal to 0, then it's truly game over, and we're going to branch ahead to this F4 8B down here. Okay, but otherwise we're going to execute this code. We've actually gone extended time, so we're going to use one of them up. We're going to decrement it by 1, and then we're going to get another counter here, 54. And this is the number of extended times used, which you could think of as maybe like lives, but I think it's better to think of it as a difficulty level. And initially it's set to 0, but we're going to check it and see if it's equal to 5, which is like a difficulty cap. Like that's as hard as the game can get, is up to level 5. And if it's less than that, actually that's one more than the maximum. I think the most difficult level is level 4, just because of the 6502, how it works. It has a branch of carry clear, which is like branch of less than. So I think that's why 5 was checked here. Anyway, is difficulty less than 5? If yes, we're going to branch ahead to here. Otherwise, it's going to load 4 into the Y. So basically, it's capped it. In case the difficulty started getting incremented very high, it brings it down to 4. And then it uses that difficulty level as an index from a short table at F564 that we'll look at in a moment. And then that value is stored in 18. And if you remember, 18 is the number of ticks per second. So this is a table containing how many ticks there are a second. Here, this is where we're finally finding that, yes, this changes. It's initially 60 ticks per second, but it changes from this table. We'll look at those values shortly. Now that we've got the new difficulty level, we're going to increment Y, that difficulty level, which was 0. Now it's gone to 1. And we're going to store that back in the difficulty level. Then we're going to reset our time. This is the BCD time value, 60. So you got a new 60 seconds on the clock, 60 units of time. And that gets stored. And then we're going to zero out the game over flag that we had set and the tick counter that counts up to the number of ticks per second. And then finally, we're going to load Y with 57 and X with 56. Actually, you notice here, Y was stored in 56, but now it's getting Y from 57. It's actually swapped the X and Y. This has got to be a bug. But when I looked at all those other routines, none of them actually seem to use X and Y. So It's being preserved here. I don't think it needs to be. And then the routine's done. So game over is cleared. Well, if it gets down to here, that is actual game over, and it does the little end of race animation. But otherwise, game over has been averted. You get extended time and to the new difficulty level. Okay, so to look at that table, that was at F564. Okay, here it is. So in hex bytes, we know that the limit is 4. So this is index 0, 1, 2, 3, and 4. And that gets into these 79s, whatever those are. But this is the table, just these first 5 bytes. Okay, I worked these out in decimal. That's actually 64 decimal, 58 decimal, 52 decimal, 47 decimal, and finally 34 decimal. Okay, so these are like 60ths of a second. So you see, when the game starts, we have 60 ticks per second. Once you've used up one extended time, the game actually gets easier for a moment, or at least a second becomes 64 60ths of a second, more or less. So it actually gets longer. And then when you run out of your second set of 60 seconds, 60 units of time, then the second length goes down to 58 60ths, 52, and so on, 47, and then a huge jump. So it's just changing by what? About 5, 6 60ths of a second at a time. The second is shrinking. The actual, again, I'm calling it a second, the unit of time is shorter. But then, whoops, I accidentally hit return. But the final one, it goes all the way down to 34, 13 64-second, nearly an extra quarter of a second is lost in that final difficulty level. So this, if the game cheats, this is where I feel like it really does cheat. And I think this is why I find it impossible. Well, I guess the game's got to end eventually, but this is where it feels like the seconds are just, they're almost like half seconds, and it's almost impossible to just keep the game going for all that long at this point. If I'm super in the zone and don't crash at all, I think I've made it up close to 300,000. Actually, that's on a joystick hack. I don't think I've ever taken this. I've probably gotten about to 200,000 on this original paddle cartridge version. There is a joystick hack out there that I used to play when I was a kid. Actually, there's several of them, but I played one of them. Okay, so if you were to patch the game, this is probably the byte, because I think once you get to this level, the difficulty stays at this. So maybe changing it to something like, 29 hex or 2A hex, another, let's do 5 or maybe here 6, less than the previous level. Oh, just going all the way down to 22 hex. That's a lot. So anyway, there we go. That's the mystery. It feels like the game cheats, but I think it was done on purpose. It's kind of that arcade game mentality where they don't want you to play forever and they want to get your quarter out. And that kind of mentality didn't go away when home computers were made and home video game consoles, even though in a way they could have, because, they already had your money. They didn't have to kill you off. But, I don't know. Just quickly look at a couple more things that I just found kind of interesting here. If we disassemble E06D, here's where some values are stored in. These are the timers. This game, interestingly, doesn't use the raster interrupts. It does not use the VIC to drive the frame rate. Instead, it uses the CIA timers the same way that the kernel operating system does to blink the cursor. So if I type the number sign 41, that's the high byte, 1A, 411A hex, here it'll convert it to 16666 decimal. Well, that's kind of a funny number. Where did they get that from? That's how often they want a tick to occur. 16,666 machine cycles, there will be an interrupt. Okay, so if we just go into basic, we can figure this out. So if we take that 16666 and multiply that by the 60 ticks per second, we get a number that is very close to a million. Taken another way, if we take a million, 3, 1, 2, 3, and divide that by 60, we get 16666.66. So if they just truncated that fraction, then that's the value. So they may not have known the exact clock speed of a Commodore 64 when they were developing this game, because it was still I think it was still kind of in prototype form. They might have been told, oh, it runs at 1 megahertz. So they took that very literally. So what this means is that rather than running at 60 frames per second or 60 hertz on an NTSC Commodore 64 or a Japanese one for that matter, or the NTSC Max machine, or running at 50 frames per second if they were syncing to vertical blank on a PAL machine, by doing this CIA interrupt, they've kind of stabilized the frame rate a bit. So the exact numbers, an NTSC Commodore 64 runs at 1022727, a little over a million. And if you divide that by 60, you see that actually you get about 17,045. Or let's divide that instead by 16,123, like they set it up. Okay, so on NTSC Commodore 64, this game's going to run at about 61.37 frames per second. And a PAL machine runs at 985,248 cycles per second. So let's divide that by 16,666. So it's going to run at about 59.12 frames per second, about, on a PAL Commodore 64. So you see the difference between those is only about 2 frames per second instead of 10. So I guess that's kind of an advantage. The disadvantage, though, is that as you play the game, you can actually see some tearing on the screen because the screen is not getting updated at the same rate as the video display, and you can see that kind of visible artifacts, tearing and so on, from the scrolling and sprites being updated at the same time that the raster update is happening. So it's got pros and cons. But again, this is a very early game, 1982. Okay, and just switching the RAM back in there. And the one last thing to look at is that E802, there are 6 unused bytes, but I don't see any reference to here from 70E66004. So I do note that it's a DDE. So I don't know if that's an Easter egg. I doubt DDE are the initials of the programmer. That doesn't sound like a very Japanese set of initials, but I guess it could be. I'm just not sure what the meaning of this is. It might be just disused, but it seems like it's just not there. Those could be pointers, like E670 would be in ROM memory, and 04, again, they're low byte, high byte format. So if we treat them as a pair, and then 0460 and 0504. And these last two are within video RAM, but I didn't see any other significance. Like I looked at E670, and actually that is, well, if I disassemble E660, I'll just disassemble a little ahead of 670. And you see this, it's all this code, and I think this is scrolling the screen right here. This is the code that scrolls the screen, just quickly copies all the character data, loading it from here and storing it there. Yeah, well, of course, the screen is scrolling down, right? So it's copying from A to 28, 28 characters, 28 hex characters, which is 40 characters. It's just copying everything down the screen. So I don't know. That doesn't seem to be of any significance, but E802. Anyway, if you can figure out anything about it, Well, that would be cooler here if we interpret E802. These 6 bytes. Maybe it's nothing. So I didn't really expect this to take multiple videos to look through it, but I've actually learned a lot during this time, not only here in the code, but in those previous videos about the Ultimax format, dumping a ROM, and so on. I hope you found it enjoyable too. I love learning stuff like this. I'm still learning after 40 years. Hey, thanks very much to my patrons for their support. Thank you for watching, and we'll talk to you next time.